Hello everybody, welcome back to Physics 425. We're back here looking at our roadmap towards understanding dilution refrigerators. In the last video, we tackled the Pauli exclusion principle. We wrote down distribution functions for fermions and bosons, and we talked about Fermi energy and the density of states. Today, what I hope to do is to start and finish a relatively long calculation of the low temperature heat capacity of a system of identical fermions, and then possibly use that to also calculate the low temperature entropy. So if we go back here, this is what our goal is, to calculate the heat capacity of a system of identical fermions at low temperatures. And so what we mean by low temperature in this context is that, so low temperature means that the system temperature is much less than the Fermi temperature. And the Fermi temperature can be defined as the Fermi energy divided by Kb. So we can use the constant Kb to convert our energy units to a temperature. Okay, so this Tf is going to be Fermi temperature. Before we start, let's just make a couple of comments here that what we're going to try to do is a pretty beautiful calculation, and what it's going to do is it's going to connect our microscopic quantum theory to something that can be measured on a macroscopic scale, to a measurable macroscopic thermodynamic quantity. Right, I can take a bath of liquid helium-3 and I can measure its heat capacity. But the calculation we're going to do is going to start with some fundamental principles that we really arrived at by thinking about wave functions in the beginning. So the results of this calculation will apply to things like the conduction electrons in a metal, neutrons in a neutron star, or the application that we're going to be particularly interested in are helium-3 atoms mixed in with liquid helium-4. Okay, one thing that's kind of interesting to note is that for conduction electrons in a metal, the Fermi temperature in this case, I think, is around 10 to the 4 or 10 to the 5 Kelvin. And so in this case, the low temperature limit, T much less than the Fermi temperature, really corresponds to room temperature. And so although we're really thinking about the low temperature behavior of systems, we can apply it to the conduction electrons in a metal at room temperature. Okay, so the result that we will get, the punchline, is that we will show that the specific heat or heat capacity of our identical fermion system is going to be proportional to T when T is much less than the Fermi temperature. So that's what we're trying to show. Okay, and so this is also the first example of us trying to calculate some physical quantity, some material property of a system. All right, so what we're going to try to do first is to write down something called the density of states, so DOS. The notation we're going to use is d of epsilon, where epsilon is energy. And so if we take the d of epsilon and multiply by d epsilon, what this quantity is going to do is it's going to tell us how many quantum states there are between energies of epsilon and epsilon plus d epsilon. And so it's called a density of states because it's the number of states per unit energy, right? So I have to multiply by an energy range, d epsilon, to get the number of states. So it's a number of states per unit energy. So if we have a system of n identical fermions at t equals 0, then all states below the Fermi energy are filled, and all states above the Fermi energy are empty. So for example, if we were to draw this occupation, so I think we used the notation n Fermi Dirac last time, and so if we had something like this, where this is our Fermi energy, then what we would find is that states with energies below the Fermi energy would be filled, and then above it would be empty. So here's 0, and this is what the t equals 0 distribution function looks like. What we're going to do is we're going to use a different notation today, so a little bit nicer to write. This f of epsilon is the distribution function, and we're going to talk about fermions today, and so we're going to use the Fermi-Dirac distribution function. Okay, the other thing you might recognize is that last time when we were talking about these distribution functions, we indicated that this line was the chemical potential mu. And so let's just make a couple of notes here. Recall that the chemical potential mu tells us the change in system energy when the number of particles is changed. So let's think about this. Let's think about a collection of fermions at 0 temperature. In that case, what we would have is, say, our first energy state would be filled with, say, 2 identical fermions, one spin up, one spin down, and then our second state would be filled, and we would keep adding particles until we filled up all the lowest energy states, until we used up all of our available particles, so the n particles that we have. And then this would be the Fermi energy up here. And then you could ask the question, well, if I add one more particle, how much does my system energy change? Well, it changes by the Fermi energy, because that additional particle is going to go into the level that's just above the Fermi energy or just right around it. So when we add a single particle to the system at t equals 0, the system energy increases by an amount of energy that's equal to the Fermi energy. And so therefore, the chemical potential is equal to the Fermi energy at t equals 0. Okay, so let's figure out a way to count the number of particles. So what we're going to do is we're going to say the number of particles in our system is going to be, we said the density of states times a energy range tells us the number of states available between epsilon and epsilon plus d epsilon. And so if we add up the number of states available from an energy of 0 up to the Fermi energy, those are all the states that are filled. And once we get to the Fermi energy, those states are empty, so they don't contain any particles. And so this is one way of counting the number of particles in our system. And so let's call this equation star, because we're going to come back to this. So this is the number of states from epsilon equals 0 to epsilon is equal to the Fermi energy. Okay. So the Fermi Dirac distribution function, which we wrote down last time, we're going to call it f of epsilon, as I said, gives the probability that at some temperature T, a state with energy epsilon is occupied. Okay, so for example, going back to this picture, at t equals 0, the probability that a state with energy less than the Fermi energy is occupied is 1. And then the probability that a state with energy above the Fermi energy is occupied is 0. And then in fact, if we took an energy exactly equal to the Fermi energy, the probability that it's occupied is 1/2. Okay. All right. So then what we could do is we could modify this expression star, a little bit. This expression was the density of states integrated from 0 up to the Fermi energy. Well, what we could do then is we could say, well, we might also be able to write this as the same sort of integral, but if I multiply by the Fermi-Dirac distribution, which is a probability distribution, then I could extend my integration range from 0 to infinity, because, for example, at t equals 0, this function is going to be equal to 1 for energies up to the Fermi energy, and then it's going to be equal to 0 above the Fermi energy. And so this calculation is exactly equivalent to equation star, because we just have a factor that's either equal to 1 or 0, at least in the t equals 0 limit. Okay. just adding to our plot of the distribution function, let's draw that same picture again. And so here is the t equals 0 case. This is the t equals 0 situation, and here is the Fermi energy. And then what you could do is you could raise the temperature a little bit. So when you raise the temperature a little bit, what happens is you end up taking the sharp step and you blur that sharp step out a little bit. Okay, and so this is, for example, maybe T1, right? It's a little bit above 0. So the way you could think of this is that some of the particles right near the Fermi energy gain enough thermal energy that they can hop out of a high energy state, or sorry, an energy state that is right near the Fermi energy, and hop into a higher energy state. And so then the occupation over here starts to build up here, and we lose some of the occupation at the top. But if you think of a particle down here at low energy, it's going to gain some thermal energy T1, but it can't hop out to a higher energy state because all of those states are already occupied, and we can't put two identical fermions in the same state. So it's really only the particles that are in states close to the Fermi energy that are able to hop to a higher energy state and blur the occupation number near this Fermi energy. And so that blurring just gets more exaggerated as temperature increases further. And so this is going to be like a T2 greater than T1. Okay, and so we can kind of define sort of a range of temperatures, and so this is going to correspond to KB times T2, and so that's sort of a temperature range or an energy range that is centered on the Fermi energy, where particles within kBT2 of the Fermi energy are able to possibly be excited into higher energy states. And that temperature range for T1 is something like this. So this is like kBT1 is the energy range that's relevant. Okay, so for temperatures much less than the Fermi temperature, only particles in energy states near the Fermi energy can be excited into higher energy states. Particles in low energy states don't have enough thermal energy and so the thermal energy that they acquire is on the order of kBT to reach unoccupied states above the Fermi energy. Okay, and so that kind of explains why some of the low temperature properties of these systems are proportional to temperature, because as you increase the temperature, the number of particles that can be excited into higher energy states increases in proportion to T. Okay, so let's just write down the functional form of the Fermi Dirac distribution, which we also wrote down in the last video. So let's remind ourselves what that looked like. So the functional form of the distribution function, the Fermi Dirac distribution, is 1 over the exponential of epsilon minus mu over kBt. And remember, it was the plus 1 that was important. Okay, good. So something else we thought about last time as well was this idea of the Fermi Sphere, where we had, remember, this k-space where we had states along kx and states along ky and kz. And at low temperature, what we're going to do is we're going to fill all those low energy states, and we're going to try to crowd around the origin, and we form this kind of 1/8 of a sphere. And so at low temperature, states up to a wave vector that is less than the Fermi wave vector are filled, where the Fermi wave vector reaches to the surface of the sphere. Okay, so another way to express or to calculate n is the following. N is equal to, we're going to integrate over k from 0 to the Fermi wave vector, and if we did this integral of just dk, when we evaluated that, what we would get is the volume of that Fermi sphere. And remember last time we said the volume occupied per state is this pi over L cubed. And so if we take the total volume of all the occupied states, divide by the volume per state, we would get the number of filled states, or the number of particles, except that we're going to put 2 particles in each state. And so this pi over L cubed is the volume occupied per k state. And this is 2 particles, 1 spin up, 1 spin down, per k state. Per k state. So just to let you know what we're going to do here, we're going to do this calculation for n. And then what we're going to do is we're going to get some kind of result, and we're going to compare it to this equation star. And so we're going to have 2 ways of calculating n, and we're going to compare the 2, and from that we're going to deduce the value of this density of states. So that's the objective here. Okay, so let's see. This n is going to be 2, and we're going to go from 0 to the Fermi wave vector. This pi over L cubed, we're going to write as pi cubed over the volume of our system. So if our system is L by L by L, its volume is L cubed. And so we get a V over pi cubed. The dk vector represents volume element. And so it's a sphere. And so a spherical shell has a volume 4 pi squared dk. So 4 pi k squared is the surface area of the sphere, and then dk is when you multiply by dk, that's the volume of a shell. But then we have to remember that we have only 1/8 of a full sphere. So we're only working in the positive, I guess, octant, if you like. Okay. And so let's see, the 2 and the 4 cancel with the 1/8, and there's one factor of pi that cancels, and so we end up with v over pi squared, the integral from 0 to kf, and then we have k squared dk. Okay, so now we're going to do some manipulations here. What we're going to do is we're going to write dk as dk over d epsilon times d epsilon. The reason we're doing this is because when we want to go back and compare to equation star is written as an integral over energy, and so we want to convert the integral that we have now to something that's not an integral over k space, but an integral over energy. Okay. D epsilon dk is d by dk, and for non-interacting particles, the energy is just kinetic energy. It's h bar squared k squared over 2m, and so when you evaluate this, you get h bar squared k over m. Okay, so therefore this dk d epsilon is the inverse of that. It's m over h bar squared k. All right. So therefore, n is equal to v over pi squared, so that prefactor stays the same. We have the integral from 0 to the Fermi energy now, because we're going to convert our integral to something that's over energy. For now, we'll just keep it as k squared. And then the dk is dk by d epsilon. And so that's m over h bar squared k. And then multiplied by d epsilon. Okay, good. So what's next? Energy is h bar squared k squared over 2m. So if you solve this for k, that's going to be 2m epsilon over h bar squared would be k squared, so then take the square root. K is root 2m epsilon over h bar. And there's a k squared and a k that cancels, and we're going to make this substitution right there. So then what we end up with is n is equal to v over pi squared, the integral 0 to the Fermi energy. K is root 2m epsilon over h bar, and then we have m h bar squared d epsilon. Okay, so what we have then is the integral 0 to epsilon f of, I'm going to reorder some things, m times v pi squared h bar cubed root 2m epsilon d epsilon. So what I want to do is I want to multiply by, I think, 2 over 2. And so this would be 0 to epsilon f v over 2 pi squared. So we've got the v, the pi squared, and the 1 over 2. And then what we have is an m times square root m. And so we'll have an m. We have 2 times square root 2, so we'll have a 2. And then we have h bar cubed, so I'm going to put an h bar squared in here. And if I raise this to the 3/2 power, that should be correct, because then we have 3 factors of root 2, 3 factors of root m, and then 3 factors of h bar. Okay, and then we still have a root epsilon and a d epsilon. Okay, good. So now what we can do is compare to equation star, which I'll rewrite, which was n was equal to the integral of epsilon f d epsilon, d of epsilon times d epsilon. And so these two integrals have the same form, and so it must be that the density of states d of epsilon corresponds to everything in the argument of the other integral, because they're both expressions for n, the number of particles. And therefore, our density of states is d of epsilon is equal to v over 2 pi squared 2m h bar squared to the 3/2 square root epsilon. And so that's one of the objectives that we had for today. And so what we're going to try to do now is we're going to try to use that density of states to calculate a heat capacity. So the next goal is to use the density of states to calculate a heat capacity. Okay, so we'll start by seeing if we can calculate the internal energy of our system. And then we can use the internal energy and a temperature derivative to evaluate the heat capacity. So U is equal to, let's see, the following. There's going to be an energy times the probability that a state is occupied, the Fermi Dirac distribution, right? So we only have to include the energy of a state if that state is occupied. And then we need to know how many states are there at that particular energy. And so breaking this down, this is the number of states with energy epsilon. This is the probability that the state is occupied. And then this is just the energy. And so we find how many states there are with energy epsilon. If they're occupied, we count them, and then we multiply by the energy of those states, and we add them up for all the values of energy from 0 to infinity. And that's the internal energy of our system. Then the heat capacity is going to be du dt, and so we could calculate it at constant volume, for example. And so if we take the temperature derivative of the internal energy that we just wrote down, it would look like the temperature dependence is going to be in this distribution function. And that's what we need to evaluate. So we're going to do a little bit of a trick here. So the first thing we'll do is we'll make the following note. first, we note that if we look at a slightly different integral, okay, so this is the same integral except we've dropped the factor of the energy. Okay, now I could change the order of the derivative and the integral, so I could equivalently write this as the following. But we just worked with this expression, right? The number of states, d of epsilon, d epsilon, times the probability that that state is occupied, and integrate over all energies. That's just the total number of particles in our system. This is n. But if we have a closed system, then the number of particles is fixed. And so really, what this is equivalent to is the derivative of the number of particles. But if the particle number is fixed, then it's not changing with temperature. And so this would be 0. Fixed number of particles in our fermion system. Okay, so then what I'm going to do is I'm going to go back to this expression for the heat capacity. I'm going to rewrite exactly the same expression, but then we're going to add something to it. Okay, so first let's just rewrite it exactly as it was. So the heat capacity is du dt, which is the integral 0 to infinity epsilon df of epsilon dt times the density of states. Okay, so that should correspond to exactly what is written in our original expression. So what I'm going to do is I'm going to subtract something from this. I'm going to subtract the chemical potential, but then I'll multiply it by this integral. And so this integral is the one that we just worked with above here, and we showed it was 0. So we showed that this was already 0. So essentially I'm subtracting 0 from the first term, and so I can do that without changing the result. But it's going to turn out to be a convenient thing to do because there's a lot of common factors in these two integrals. So I can combine the two, and what it looks like is epsilon minus mu times the derivative of the distribution function with respect to temperature times the density of states. Okay, good. So this is our current expression for our heat capacity. We have a derivative of a distribution function, and we know what that distribution function looks like, and so we should be able to evaluate that derivative. So let's try to evaluate df dt. Okay, so df of epsilon dt is d by dt of, so 1 over the exponential of epsilon minus mu over kbt plus 1. Okay, so we have to use, a bunch of product rule and chain rule and so on. But, so the first thing that would happen is you would get the square of the denominator. Plus 1 squared, and you'd pick up a minus sign. And then you take the temperature derivative of what's inside, and so we're going to have to multiply. So I'll write it over here. We're going to have to multiply by, let's see, we're going to get epsilon minus mu over kb, and we'll have t squared, and we'll pick up another minus sign, and then we'll get the exponential back again. So I think that's probably right, and we can cancel the two minus signs. And so therefore, just let's write it a bit nicer over here. We're going to have epsilon minus mu over kb t squared exponential of epsilon minus mu over kb t over the exponential of epsilon minus mu over kb t plus 1, and all of that squared. So I think that's what it is. So that's kind of a mess. Before moving on, I just want to notice one other thing. What if we were to take the energy derivative of this distribution function? Okay, so that's going to be d by d epsilon of the distribution function, which is 1 over the exponential of epsilon minus mu over kb t plus 1. And the result is going to be pretty similar. We're going to get the denominator squared, and we'll pick up a minus sign. And then we take the derivative of the denominator, we'll pull out a 1 over kbt, and then we'll get the exponential back, but no minus sign this time because the energy is in the numerator inside the exponential. And so if we compare these two results, you know, some of the results are pretty similar. In fact, there's a big common factor, and we can notice that this df dt is the same as df d epsilon, except there's a negative sign, and there's an extra factor of epsilon minus mu, and it's a 1 over t squared instead of 1 over t. And so there's this relationship between these two derivatives. So what we're going to do is if we call this number sign, we'll go back to our heat capacity expression, and we're going to replace this df dt derivative with number sign, which is going to convert it to a df d epsilon derivative. Okay, so let's do that. So our heat capacity then is going to be, there's an overall negative sign now, integral 0 to infinity. We already had a factor of epsilon minus mu, but now we get another one, so it's going to be squared. We pick up a 1 over t, and instead of df dt, we have df d epsilon. Then we have d epsilon, density of states times d epsilon. Okay. So let's think a little bit now. I'm going to draw this picture again that we've drawn a few times. This is the distribution function at low temperatures. So this is at temperature much, much less than the Fermi temperature. Notice that we've got a energy derivative of this distribution function. And so if we were to plot that energy derivative of f, we would notice that, well, at very low energies, the thing is constant. And so the derivative of a constant is 0. So we get 0 at low energies. And then at high energies, it's again constant. And so we're going to get 0 again when we do that derivative. And then right at the Fermi energy, there's a step. And so there's like a discontinuous step. And so that means that this derivative spikes up. It becomes a very huge value just at the Fermi energy. And so if we think of what the integral means, it's kind of adding up all the contributions from a wide range of different energies. But this is huge only at one particular value. And so because it's so strongly peaked, the contributions at different energies are relatively weak. And so we're going to make an approximation by taking this density of states and including the value only at the Fermi energy, which is the most important energy in our calculation. Okay, so at low temperatures, this derivative with respect to energy is strongly peaked at the Fermi energy. I've been using capital E for the Fermi energy. Okay, so therefore, in the integral, we can replace the density of states with the value at the Fermi energy. Okay, so that is an approximation, but it's going to make our calculation simpler. So we're going to have minus. When we put in the Fermi energy to the density of states, that just becomes a constant, and so we could pull this out. And then we have the integral from 0 to infinity of the other stuff stays the same. But now we have this product df d epsilon times d epsilon, and so this is df. So we're going to change now from an integral over energy to an integral over f, the distribution function. So we have to think about the limits of integration. So note that when epsilon is equal to infinity, the upper integration limit, at high energy, the probability that a state is occupied is 0. And when epsilon is equal to 0, very low energy, the probability that that state is occupied is 1. So CV is approximately minus the density of states at the Fermi energy. We have a 1 over t that we can take outside. So we go from f equals 1 to 0. And then we have epsilon minus mu squared. And then we have df. If we switch the order of the integration limits, we get rid of the minus sign that's out front. Okay. And so now we have to be a little bit careful here. Let's remember the form of the distribution function. It was the exponential of epsilon minus mu over kbt. And then it was a plus 1, right? And then we take the inverse of all of that. Okay, so if that's the value of the distribution function, then 1 over f minus 1 is equal to this exponential. If we take the ln and then multiply by kbt, what we're left with is epsilon minus mu. And so what we're going to do is we're going to substitute this into epsilon minus mu, and then we'll have to square it. Okay, so let's see. Our heat capacity then is the density of states at the Fermi energy divided by T, then we had the integral 0 to 1, and then we had epsilon minus mu squared, and so that's going to be kBT squared. And then we have the ln of 1 over f minus 1 squared in df. So that finally, the heat capacity is kB squared. Then we have a T squared divided by T, so we get a T. Then we have our density of states at the Fermi energy. And then we have this integral 0 to 1 of ln 1 over f minus 1 squared. This integral has an analytic solution. Believe it or not, it's pi squared over 3. And so this is an exact solution. Okay. So you can kind of see the result already that we wanted to get. We wanted to get that the heat capacity was proportional to temperature. And so we have that. And so what we're going to do now is we're just going to try to rewrite this in a neater form. And so first we'll deal with the density of states. So the density of states at the Fermi energy had this form that we worked out. It was V over 2 pi squared, and then we wrote it in this way. 2m over h bar squared to the 3 halves. And it was square root of energy, but now we're working at the Fermi energy, so we'll just write it as square root EF. Also recall that the Fermi energy was h bar squared over 2m, 3 pi squared n over v to the 2/3. Okay, so if we wanted to, we could write the Fermi energy to the 3 halves power, then would be h bar squared over 2m to the 3 halves, and then it would be 3 pi squared n over v. Okay, so let's put some of the stuff into our heat capacity. So we have kB T, and then we had, where was it? It was up here, kBT, and then it was the density of states. And the density of states we wrote down as V over 2 pi squared 2m h bar squared to the 3 halves. Then we have the square root epsilon f, but first let me put in the pi squared over 3. So pi squared over 3, and then we have square root of the Fermi energy. Okay, let's just sneak in a factor of 1. And our factor of 1 is going to be n over n, so that we can write CV is equal to kBT, it's kB squared. It's kB squared here. So I missed that square. So kB squared T, and then what we'll do is we have a factor of 1/2, which we'll write, and then we have a factor of n in the numerator, and then we have V. We have a 3 pi squared and a 1 over n, and then we have the 2m h bar squared to the 3 halves, We still have a pi squared hanging out, so we'll put in a pi squared here, and then we have root of the Fermi energy. And all of this stuff is the inverse of the Fermi energy to the 3/2 power. So this is 1 over the Fermi energy to the 3/2 power. So canceling everything, then we have CV is equal to KB squared times T N, and there's a pi squared over 2, and then we have 1 over the Fermi energy. Okay, so at last, pi squared over 2. Let's write this as KB squared T. There's an N, and the Fermi energy we could write in terms of the Fermi temperature. So we could cancel 1 factor of KB, and so the low temperature heat capacity of identical fermions is CV is equal to pi squared over 2 N KB T over TF. And that is our main result. Heat capacity of our low temperature fermion system of identical particles is proportional to temperature, and now we've worked out what that prefactor is. Okay, so that's a long calculation, but it's pretty neat in that what we did is we started really from a quantum mechanical theory, and now we've derived a thermodynamic quantity that you could go into the lab and measure. All right, so that's where we'll stop for today. Thank you very much, and we'll talk to you next time.